Well, hello everyone. Welcome to my talk. I'm Joel Walker. I'm with Pump, and I'm going to be talking today about how we use ClickHouse, how ClickHouse helps us ingest cost visibility data. So there's three main things I'm going to talk about here. I'm going to first give you guys a brief overview of what Pump is, what our product is. I'm then going to talk about the architecture of kind of how we built the product. And then I'm going to talk about a few of the challenges that we ran into along the way and how ClickHouse helps us solve these challenges. And so what does Pump.co do? Pump optimizes your cloud. If companies join us and we save them money in a few ways, one of the big ways is that we purchase commitments. So in AWS, these are reserved instances and savings plans. We look at your past usage. We can match that up with what AWS is offering. And we can optimize, we can purchase commitments on your behalf. That's one of the things we do. The second thing we do is that we give you visibility into your cloud spend. And this is what I'm going to be talking about today. This is a new product that we built about 6 months ago, and it's built on ClickHouse. So what is cloud spend? You guys, I don't know, some of you might be familiar with this. This is a screenshot of Amazon's Cost Explorer. If you are on Amazon, you can go into Cost Explorer and see what you're spending by day, broken down by service. Cost Explorer is good, but it's not great. It doesn't give you high granularity insight into where your costs are breaking down. And it doesn't really include user tags. And so users can tag their resources with different key value pairs. And in Cost Explorer, they're not able to see that. This is what we built Pump View for, is to give the users more visibility into these things. And we want to provide a unified framework with GCP, Azure, all these things where users can see their costs in one place. So I'm going to give you guys a short demo of what this looks like. So this is Pump's backend. Their dashboard. You can see here that the costs are broken down by service. You can see each day what the customer is paying. And you can break it down by whatever you want. You can break it down by region. You can break it down by usage type. There's a lot of usage types. The front end is a little slow. You can break it down by any of these things. You can filter. So you can see in for example, a specific region. I only want to look at my US West 2 spend. And now you're going to see a breakdown of your costs in that region. So this is the general idea. And all of this is driven under the hood by ClickHouse. So what does this query structure look like? This is an analytical query. This is exactly what ClickHouse is good at. You're summing up costs from a table. You're filtering by a few things. You're filtering by company ID. You obviously only want to give a certain company access to their data. You're filtering by a time range, a begin and end. And you're filtering, and any other filters that the user selects. And typically, you're grouping by something. You're grouping by service or region or usage type. So why ClickHouse? At Pump, we use Postgres quite extensively. And that was the logical option to choose because we use it already. But Postgres has some challenges. First and foremost, Postgres is optimized for transactional data. It excels at being consistent, giving you a consistent view into your data at any point in time. ClickHouse is optimized to split up data ingestion and data analysis, so writing and reading. When you insert data, it shouldn't slow down your queries, and when you're querying, it shouldn't slow down your inserts. ClickHouse just scales much better. Postgres, we ingest about, I'll get into the numbers, but billions of records every day, and that's something that Postgres would have a hard time doing. This is a high-level overview of what's going on in the system. We ingest data from 2 cloud providers right now. They give us periodic exports. These exports happen every 8 hours for AWS. they get put into S3 in a Parquet format, and we have a job that picks these up and inserts them into ClickHouse. I'll get a little bit more into the source and aggregation table, but once they're in ClickHouse, we do some tracking in Postgres to say what is the active version. And I'm going to talk a little bit more about this, how Postgres interacts with ClickHouse, but this is necessary in order so that we can present a unified view of the data, even if we're in the middle of inserting data or deleting or cleaning up old data. And then obviously we have a front end and a back end that's giving the user access to this data. So I'm going to talk about 4 challenges that we had to overcome when we were building the system. And I'll go through each of these in more detail. The first one is semi-sparse records. What we ingest from AWS is at its core sparse data. Different line items types are going to have different fields. AWS is going to have very different fields than GCP. And any line item can be annotated with user tags. And so any user tag that's applied to, say, an EC2 instance in AWS is going to end up here. And I'll show you that on the next slide. But just to give you a scale of what this data looks like, this represents 1 hour. It's a very small amount. I just picked this one at random. But everything you do in AWS is tracked, and I guarantee you're going to be charged for it. This is 2 millionths of a penny. It's
cost more to generate this data.
Yeah, probably. Yeah, this is a load balancer in US West 2. And then this is the end of that record. You can see here what's interesting is this resource tag. This is a user tag that was applied that tells what this load balancer was, I suppose in this case, what it's running. It's running Nginx. And yeah, the key here is that this doesn't fit into a tabular database. This doesn't fit nicely into a column because each company is going to have their own tags. So how do we ingest this? Well, ClickHouse has a map type. And so you could just dump all of this data into a map from strings to string, a map from string to float, because there's some strings in there, there's some numbers. But this would be very slow because of the way that ClickHouse queries this map is it's going to just read the column and search through it, checking each, loading from I/O this whole blob in order to check if the field matches what your query is. So the solution that we came to was to shard our fields into a number of columns. We use 8 columns for this string. We use a map from string to string, and there's 8 of them. This is showing 4 of them. And we use a hash function that is simple and fast. It's implemented both in Python and ClickHouse. And so in Python, when you're looking up a specific field by key, you know exactly what column you need to look into. And this cuts down the data that you have to read by 8 times. And so what this looks like, this is the first column, second column, third. This is the last one. And then you notice that all these are string columns. And so we have the same thing for the float or the number columns. Usually the number columns are not being filtered on. They're being aggregated. They're being summed. And the string columns are being filtered or grouped by. And so that's the difference here. So this really helps us one of the things that make ClickHouse fast is its I/O, right? If you can minimize the amount of I/O, ClickHouse is going to get faster. And this helps us cut down the I/O. Now, ClickHouse does have JSON, and this was launched right after we completed this project. So JSON is the answer here, especially for our use case, because a lot of the fields are the same, and so they fit nicely into their own columns. All right, the second challenge that we had to overcome is the ingestion volume. As I said, AWS publishes its data into S3 as Parquet files. And we get a trigger when that happens, and we kick off a job to insert into ClickHouse. This is actually very straightforward with ClickHouse. ClickHouse has an S3 function that reads directly from a Parquet file, and we can just do some transformations and insert it directly into across data records. So we insert about 5 billion records every day. It's not Cloudflare scale, but it's something. It's about 5 terabytes, and ClickHouse is very fast. It takes about 40 seconds to ingest, on average, each ingestion event. So this is a scale of the data in our table. There's about 55 billion rows currently. The third problem that we had to overcome is atomic updates. As I'm sure a lot of you know, ClickHouse is optimized for append-heavy workloads. What we're doing here is more of an update action, because when AWS publishes a new month of data, it replaces the old one. So here's some things that can happen. Let's say this is the old version of data, and AWS publishes a new version, version 2. A record can be deleted. This CF57 was deleted. These 3 records were appended, and the first 2 were left unchanged. This presents a problem, because how do you ingest this? There's a few methods. If you first insert the data, and then you clean up the old data, the user's briefly going to see costs that are too high. The sum is going to return. It's going to operate over both the old version and the new version, and the cost will be too high. If you delete then insert, it's just the problem in reverse. The user is going to see costs that are too low. ClickHouse has these things called replacing merge trees, which are great, but they're for replacing individual records. An individual record will be seen by ClickHouse and basically grouped by that record, and your queries will only show the latest version of that record until the old one's cleaned up. This works great, but it doesn't really work for deleting records, because AWS could publish a new version that omits some records. ClickHouse also has partitions. Partitions support atomic updates. They are, I assume, under the hood implemented with just linking the file and swapping those links. So they're atomic, but we have over 5,000 partitions, and that number is only going to grow as months go on, as we add more customers, so on and so forth. And so partitions are meant for smaller workloads. I think the ClickHouse docs recommend 1,000 to 10,000. So this is kind of pushing the boundary. So the solution that we came to was that we store live mutations in Postgres, and we filter when we're querying ClickHouse. What does that look like? So Postgres, like I said, what it does well is transactionality. And so once we insert into ClickHouse, we have 2 versions. And in Postgres, then we do an atomic swap to read from, initially it's reading from version 1, and now we say the live version is now version 2. And in Postgres, this is atomic. And so any queries from Postgres is always going to give us a consistent set of mutation IDs. Mutations are what we call these versions internally. And so first we're reading from Postgres. We're saying what are the mutations that are live. And because Postgres is transactional, this will always be consistent. And we use that to filter what we're reading from ClickHouse. All right, the fourth, final, and most significant challenge we had to overcome is interval queries. Interval queries are hard. If you guys remember from the first slide, this is the same query. This isn't quite what you would expect. We're saying, look for records where the begin date is less than the end date of our query, and the end date is greater than the start date of our query. What is this? This is trying to find records that overlap with the query. And it's a little weird. Let's say you're querying for July. You might have a 3-year savings plan, which is a record that AWS publishes, and it overlaps barely with your query, with a start date very far in the past. And you might have a similar thing with a start date very much in the future, or you might have that 1 hour 2/millionth of a penny elastic load balancing charge that we saw earlier. All of these need to be returned by this query. ClickHouse uses order by in order to optimize its queries. But what do you order by in this query? If you order by the begin date, this is going to be very far away from this 3-year savings plan. And if you order by the end date, a savings plan that ends very far in the future will not be close to each other on disk. It's not easy to optimize this query. So what we do is we do a normalization step. If you remember in the architectural diagram, there was an initial ingestion, a source table, then there was an aggregation table. This is the step that reads from the source table and inserts into the aggregated table, the normalized table. And there's 2 things that happen here. There's a few more, but there's 2 things that I'm going to mention. The first thing is splitting up of the records. You can see here that we have a record that's a year long and for $1,000. And we split it up into each day. The end goal is that every single record in the aggregated table has the same length. And so we split this up into 365 records and insert them into the aggregated table. And we do the same thing with the other way around, aggregation. So I would say the majority of the records that AWS publishes are 1-hour records. And so aggregating them into daily intervals, number 1, it cuts down on the data that has to be searched. And number 2, again, it gives these consistent intervals so our queries can only look at the begin date of the records. So this is how it was before. We're looking at both the record begin and the record end. And now we're looking at only the record begin. And we know that the record end is always going to be 1 day before the record begin. And so this makes our order by place data locally next to each other that is going to be accessed. So that's it. That's the challenges that we have overcome so far. There's more work to do. We want to expand to more cloud providers, Azure data. We want to start trying out ClickHouse's full text search. One of the things that we do have in Postgres right now is I think it's called TS Vector, TS Query. It's their version of a text search. So if the user is typing like US West, we can tell them, here's probably what you're searching for. You're searching for this filter. You're searching for the region filter with this value. We want to move that into ClickHouse because it is a lot of data. It's one of our biggest Postgres tables. And ClickHouse will be quite a bit faster. And finally, scatter-based aggregation. The aggregation step that I mentioned is more of a gather operation. It's generating the aggregated data for a certain month, which involves this scan that could go back 3 years. We want to do more of a scatter-based aggregation in order to optimize that aggregation step. That's all I have. Any questions? It's hard to do a apples-to-apples comparison. I would expect it to be cheaper. Definitely the ingestion is far cheaper. The aggregation step that we're doing is probably the bulk of our costs right now. But Postgres would most definitely be quite a bit more expensive. That's a good question. Auto-scaling is something that we take advantage of when the ingestion runs, especially for some of our larger organizations. We have about 600 ingestions every day, but some of our larger organizations are disproportionately more. And so we want to be able to auto-scale when those happen and then come back down when there's no ingestions running. And so that's something that ClickHouse Cloud is good at, and we take advantage of that.